Welcome to the debate. When we think about how to build a reliable system, we usually think about classic machinery.
Right, like physical engineering.
Exactly. Take like a vintage race car. The architecture is fundamentally modular. You've got the chassis and, you have the engine. You can pull that entire engine out, put it on a stand, tune it, completely rebuild it, and the frame remains untouched.
The boundaries are absolute.
Right. And for a long time, we've built software the exact same way, especially when it comes to the web. The network transport layer is basically the chassis. It just holds the connection. And the application logic is the engine doing the actual thinking.
And, there is a deep, fundamental comfort in that separation. We like our boundaries visible, categorized. It's sort of how we keep complex systems from just collapsing under their own weight.
But then you step into the bleeding edge of modern server performance, and suddenly that modularity starts looking less like a feature and more like a massive artificial bottleneck.
Which brings us to today's material.
Yes. Today, we are looking specifically at gnosis-uring, which is the native Rust transport for Gnosis. Based entirely on its recently documented architecture and the benchmark snapshots from March, April, and May of 2026, we're faced with a really profound architectural question.
The core disagreement.
Yeah. Does the deep integration of transport layer mechanics, like, raw socket polling, with application layer concerns like cryptographic routing and hardware attestation, represent an elegant, necessary evolution for peak performance? Or is it a dangerous blurring of boundaries that risks systemic fragility?
That's the question.
I will be arguing that this hyper-integrated architecture is the optimal, evidence-driven path to maximizing modern secure workloads.
And I will be arguing that overloading the transport layer with complex application logic, things like middle-out collapse tables, certified topology tuples, and external hardware binaries, creates a monolithic architecture that sacrifices clear system boundaries for raw speed. It is the absolute definition of diagnostic muddy waters, I think.
Well, let's lay out exactly why we hold these positions, starting with the traditional separation of the network layer and the application layer. When I look at the classic open systems interconnection model, the OSI model, I see a relic.
A relic? That's a strong word for the foundation of modern networking.
Passing data from a network socket up through multiple abstract software layers just to reach the application, it's a massive waste of time. And if you want proof, you don't need to look any further than the massive April 2026 benchmark leaps in gnosis-uring.
The throughput numbers were high, yes.
They were astronomical. Even on the macOS blocking fallback path, which, remember, isn't even the fully optimized Linux path, the system hit over 153,829 requests per second for plain text. And basically the same, like 153,740 requests per second for JSON payloads on just 4 threads, 64 connections.
Which again is a huge number.
It is, and that throughput doubling was achieved precisely because the system stopped respecting those old boundaries. They integrated what they call the X topology token cryptographic admission gate directly into the transport layer.
Right, the admission gate.
And they did it using zero allocation byte window sliding. For those listening, normally your network card gets a packet, hands it to the operating system, which copies it into a buffer, and then hands it to your app, which copies it again. It takes time, it takes memory.
It's expensive.
Exactly. Byte window sliding just points a virtual magnifying glass at the memory where the data already sits and just slides it over the relevant bytes. No copying. It operates in O of 1 constant time. By doing this right at the socket level, the system doesn't waste cycles passing buffers up a virtual stack. Performance at this scale absolutely requires collapsing the boundaries between the chassis and the engine.
Look, I acknowledge those benchmark numbers. And yes, zero-copy architecture is incredibly fast. We all know that. But performance metrics shouldn't blind us to architectural bloat.
You think zero copy is bloat?
No, I think what gnosis measuring is doing under the hood is bloat. When you actually look at the feature set, it is staggering what this simple, quote-unquote simple, transport layer is being asked to do. It isn't just moving bytes anymore.
It's doing a lot more, sure.
It is managing a native raw path AON UDP leg alongside TCP. It is resolving natively compiled routes carrying incredibly complex 10, 12, 17, 22, 43 topology tuples. It's even running external C binaries to gather hardware trusted execution environment quotes, like SGX and TDX, all within the socket daemon.
Right, natively.
But that chassis and engine is one approach, while it absolutely yields microsecond optimizations, forces the transport layer to manage deep business logic complexity. That fundamentally risks maintainability. It creates this sprawling error surface that is going to be an absolute nightmare to debug when things go wrong in production.
I hear the concern about maintainability, I really do, but I think you have to look at the environment these servers are actually operating in. Let's look at exactly how this transport layer handles multi-protocol racing.
Let's do that, because this is where the over-engineering really starts to show. Gnosis-uring utilizes a same-request mixed-race architecture,
Which is brilliant.
which means it takes a single logical request from a client and duplicates it. It sends one copy over a standard TCP wire and another copy over a raw UDP wire simultaneously, just to see which one arrives at the server first. To manage this race, the server implements what the documentation calls a bounded middle-out collapse table.
I actually love the middle-out collapse table. Let me give an analogy for the listener here. Imagine you have a high-profile VIP at a restaurant, and you want to guarantee their food arrives as fast as humanly possible.
Okay.
You don't just put in one order with the kitchen. You give the exact same order to two different chefs at the exact same time. Whichever chef finishes the plate first goes to the VIP, and the kitchen quietly throws the second plate in the trash. That's what this collapse table does. Its entire job is to cheaply vent or, drop the later duplicate request so the server doesn't run the full hot path twice.
It's a great analogy, but let's follow it through. Throwing a perfectly good plate of food in the trash is wasteful. I just don't buy that this massive redundancy is necessary for standard server operations. Look at the cloud build race frontier.yaml evidence in the material.
The frontier sweeps.
Right. The system actually requires a focused sweep, playing with true requester-side hedge delays just to find what they call the diversity waste frontier.
The diversity waste frontier being the exact millisecond threshold where the UDP packet wins often enough to justify sending it.
Exactly. They literally have to sweep delay parameters to figure out the exact point where firing off that second chef's order isn't just completely wasting network resources. You are building a massive complex tracking table into a raw network listener just to clean up the mess of your own redundant requests.
But you're looking at it through the lens of a standard web server, not a hyper-optimized network. Think about modern financial high-frequency trading networks.
High-frequency trading is a very specific use case, though.
But it's the paradigm here. In environments where absolute minimum latency is the only metric that matters, redundancy isn't waste. Redundancy is survival. You fire on all cylinders because packet loss or a microsecond of jitter on one path is entirely unacceptable. And what makes now gnosis-uring brilliant here is the shared laminar identity.
The cross-transport identity, yeah.
Right, because the request carries a shared laminar identity across both the TCP and UDP transports. The server can correlate them natively at the lowest possible level. The socket knows they are the same request before the application even wakes up. And the system handles this beautifully.
Does it, though?
It does. If you look at the March 2026 benchmarks for the Linux IO-uring pipelined HTTP path, it pushed 5.1 million requests per second at a pipeline depth of 256 on an 8-thread worker. 5.1 million. The transport matrix can clearly handle this collapsed table complexity natively without buckling.
Because of the kernel.
Yes, it's utilizing kernel features like SU poll, where the kernel is actively polling the submission queue so the application doesn't have to constantly context switch. The kernel is doing the heavy lifting.
But is it just the kernel doing the heavy lifting? The material notes that in the deepest benchmark legs, specifically that mixed TCP and UDP race at depth 256, the benchmark client reported 5,479 socket timeouts.
Well, sure, but
Now, to be fair, the material clarifies these were client-side timeouts, not server panics. But it absolutely proves my point about the diversity waste frontier. You are generating immense network weather. You are saturating buffers, dropping packets, and relying on a highly complex collapse table to sweep up the debris. It's brittle.
I wouldn't call a system brittle if it successfully completes the benchmark without a single server panic under that kind of punishing load. If anything, it proves the bounded collapse table works exactly as designed. It vents the duplicate leg cheaply without crashing.
Okay, but let's take a step back. Let's assume for a moment that throwing away duplicate TCP and UDP packets in the socket is justifiable for the sake of latency. Does that justify pushing higher-level routing certificates into the transport daemon?
I think it does.
If giving the socket the power to drop packets based on speed is a half step, giving it the power to route them based on application logic is falling off a cliff. And that brings us to the May 2026 Certified Braid Route Collapse updates.
The routing collapses are honestly where I think the architecture truly shines.
I respectfully disagree. Look at what is actually happening here. The built-in compiled routes in gnosis-uring now carry a certified 10, 12, 17, 24, 43 tuple.
Yes.
And what is in that tuple? A pressure-weighted interfere port metadata configuration, index terminal closure family members, rejection anchors for bounded valid but inexact members, and a pressure-weighted stride total.
Wait. Let's stop and break that down for the listener, because that is a lot of incredibly dense terminology.
It is. That's my point.
But let's explain it. When we talk about a 10, 12, 17, 22, 43 tuple in this context, we are basically talking about a cryptographic passport. Normally, a request comes in, the server looks at the URL, and then it queries an internal routing table or database to figure out where that request is allowed to go. That takes time.
Standard routing, yes.
Right. But here, the routing map, the permissions, and the fallback paths are all baked directly into the data payload itself. The passport tells the bouncer exactly which rooms it's allowed to enter, cryptographically guaranteed.
That is a perfect explanation of the tuple. But my question is, why does the bouncer at the front door need to know the entire family history of the person entering? A transport worker is essentially just a piece of code that owns a TTP listener. It calls bind on a network port. It should not be responsible for calculating pressure-weighted 43 interfere strides certified by Gamut Braid. This is a severe conflation of concerns. Why does a raw network socket need to execute application domain logic?
Because the socket is where the data physically arrives. Every nanosecond you spend passing a buffer from the socket up to some separated, pure application routing layer is a nanosecond wasted. I am going to point you exactly to the May 2026 micro-benchmark data on this.
The dispatch-only routes.
Exactly. The selected topology admitted path against the route chain fallback achieved effectively parity 3.612 nanoseconds per iteration versus 3.588, and it got a 1.1473x speedup on the Tech Empower plain text handler. They shaved the time down to 37.037 nanoseconds per iteration from 42.492.
Saving 5 nanoseconds per request by polluting the transport layer?
5 nanoseconds might sound trivial to a casual developer, but when you are scaling to millions of requests a second, those nanoseconds compound into massive compute savings. The diagnostic mode isolates this perfectly. Exact route lookup was just 29.168 nanoseconds per iteration. Because gnosis-uring pushes this logic down to the metal, it natively caches the HTTP date function and epoch-cached plain text headers.
The static caching is interesting, yes.
It's brilliant. It natively handles file-back static caching instead of allocating new memory for the same header on every single request. The socket knows exactly what to serve without ever waking up the rest of the application. The empirical evidence proves this efficiency is undeniable.
I don't deny the efficiency, but have you considered what happens when the application topology actually needs to change? Your transport daemon is now intimately coupled to the specific structure of those Gamut Braid certificates.
Well, you redeploy the config.
But if you decide to change your routing theory or update your application structure, you have to rewrite your network listener. That is the exact opposite of modularity. If there's a bug in how your application routes data, it could literally crash your network port. But, and this is the kicker, even that routing logic pales in comparison to the most extreme example of this architectural blending.
You're talking about the security boundaries.
We aren't just talking about routing anymore. We are talking about the transport layer, acting as a trusted execution environment attestation authority.
Ah, the confidential build.
Exactly. The dockerfile.confidential. If routing is a slippery slope, this is where the system completely abandons the concept of software layers. Let's look at what gnosis-uring is doing here. At startup, the network transport executes external C binaries. It is reaching out via Aon Runtime TE Quote Provider CMD to DevSJAX Enclave or Dev TDX Guest to fetch hardware TE quotes.
Hold on, let me jump in as a proxy for the listener here. If you're listening to this and thinking, why on earth is a network socket fetching hardware execution quotes? You aren't alone. It sounds completely counterintuitive.
Highly counterintuitive.
Right. But in a normal system, a trusted execution environment, a TEE, is a secure area of the main processor. It guarantees that the code and data loaded inside are protected with respect to confidentiality and integrity. The hardware generates a quote to cryptographically prove to an external party that the software is running in this secure enclave.
Right. And conventionally, your security or application layer handles that verification. But gnosis-uring has the socket listener doing it. It takes FP48 evidence from bitwise cache, FP48, which is basically fingerprinting data from the execution environment. It mirrors that evidence into a top-level braid certificate, and then it derives a SHA-256 runtime binding hash.
Which binds the network to the hardware.
Yes, but it feeds that hash directly into native reactor handle grants. You are making the lowest level network listener responsible for deriving cryptographic evidence bindings. If that math hangs, your entire server goes dark. This turns a transport layer into a monolithic security bottleneck.
I don't see it as a bottleneck at all. I see it as the ultimate failsafe. Think about the mechanics of network security. Where is the absolute best place to drop a malicious or unverified request?
Ideally, at the edge of the network.
Exactly, at the socket edge. If your source evidence drifts, meaning if the hardware environment is suddenly no longer trusted or has been compromised, Forge can feel closed immediately at the native socket level. The application engine doesn't even have to wake up to realize it's been compromised.
But the socket?
If you wait for the application layer to verify the hardware quote, the potentially malicious packet is already inside your house. The socket simply stops admitting traffic at the door. By owning the attestation process, the transport layer provides unprecedented, honest boundary visibility.
Honest boundary visibility. That is a fascinating phrase from the material. But is it honest if the boundary is completely blurred? The network listener isn't just failing closed. It is actively publishing a live JSON braid collapse benchmark report natively at Aon braid-collapse bench. It is publishing exact mass and leakage accounting. I have to ask, why is the socket daemon doing mass and leakage accounting?
Because the socket is the only component in the entire machine that actually knows exactly how many physical bytes have crossed a wire. If you separate that accounting into an application layer, the application can only guess based on what the socket tells it after the fact.
But it's building schemas for it.
By exposing the exact mass and leakage accounting natively, the transport layer guarantees that the accounting is cryptographically bound to the physical hardware execution. A separated application layer simply couldn't guarantee that level of physical truth at speed. It's entirely self-contained and provably secure.
Self-contained is one word for it. Monolithic is another. Think about what we are discussing. You have a Rust daemon that is doing system-level polling, tracking fixed file registrations, manually managing buffer pools for UDP races, evaluating cryptographic passports, negotiating hardware enclave quotes, and serving JSON benchmark schemas.
It's busy.
Software engineering has spent 50 years developing principles of separation of concerns precisely so that we don't build systems like this. When a bug inevitably occurs in the evidence derivation, it won't just throw a 500 error, it could crash the TCP listener entirely. That is the definition of systemic fragility.
But that's precisely why it's built in Rust. The language's strict memory ownership models prevent exactly those kinds of systemic crashes. And we know it is stable because the metrics prove it. The transport layer honors cache headers natively. It pipelines HTTP requests that utilizes advanced kernel system calls like splice. It is an orchestra of kernel-level optimizations that can only play together effectively if there is a single conductor.
I don't deny this system is fast. It is blindingly fast, but I worry about long-term sustainability. The material itself notes that even the static fixture used in the cloud build is just a tiny, easily compressible index.html file. We are pushing so much complexity down to the bare metal that we are losing our ability to reason about the system abstractly.
It absolutely demands a higher level of engineering, I'll grant you that. But let's summarize where we stand in light of this architecture. I look at the benchmark snapshots. I see this system pushing 5.1 million pipeline requests. I see 010 copy cryptographic admission, sliding windows. And to me, that is empirical proof. The evidence demonstrates that tightly coupling kernel features directly with application topologies and hardware TE attestation is the undeniable future of high-performance, secure systems.
And I will concede that the raw speed is extraordinary. The throughput numbers from April and May of 2026 speak for themselves. But I maintain that the architectural cost is far steeper than those benchmarks imply. Features like bounded middle-out collapse tables to sweep up duplicate UDP requests, or embedding FP48 evidence verification directly into a socket daemon, represent a density of logic that severely challenges our most reliable software design principles.
It seems clear that as kernels and applications continue to evolve, the exact placement of that boundary between chassis and engine is going to remain highly contested. It is a fascinating evolution to explore in this material.
Truly, it challenges everything we take for granted about system design. I think there's a lot more to explore here as these systems mature.
It really brings us right back to that classic car. For a century, we've known exactly where the engine stops and the chassis begins. But if fusing the frame directly into the combustion chamber is the only way to break the land speed record, well, you have to wonder if the old boundaries were just holding us back all along.